In this exercise, we're going to graph a rational function, f of x equals x to the fourth over 50 times x minus 3. And we're going to follow our procedure now. So I have my step-by-step procedure for graphing rational functions, and we're going to go ahead and apply that. So you can take a look at that separately. So let's get started here. Now I set things up a little bit ahead of time for myself to make it easier to write down. I do have a table of values here if I can fill in if I need it, and I have a graph grid set up ahead of time where we're going to start plotting below. So first step is look for vertical asymptotes. And to do that, because this is in reduced form, we can just set the denominator equal to 0. And that's going to be just when x minus 3 is equal to 0, or x equals 3 is a vertical asymptote. So I can go right ahead to my grid here that I've set up. And I know there's this vertical asymptote to the graph at x equals 3. And now step 2 is we're going to check for horizontal. And there can only be one if there is one. But here, notice that the degree of the numerator, or the p function on top, if we think of this as p over q, is greater than the degree of the denominator. The degree of the denominator is just 1, right, x to the first power. So there's no horizontal asymptote. Okay. All right, so we have no horizontal asymptote. Step 3 is the x and y intercepts. So the y-intercept is when x is equal to 0. If I calculate f of 0, I get 0 to the fourth over 50 times 0 minus 3. That's 0 over negative of 50, which is just 0. So one point that I have on my graph is 0, 0. And, 0, 0 is a point that's both an x and a y intercept. Let's see if we have any other x-intercepts here. If I set y, or the function value, equal to 0, right, the output, 0 equals x to the fourth over 50 times x minus 3. And the only way a fraction can be equal to 0 is if the numerator is equal to 0. And if you don't want to take that shortcut, you can multiply both sides by the denominator. Denominator will cancel on the right. We'll have 0 on the left. So I just get x equals 0. And actually, that just gives me that point 0, 0 again. So there isn't a whole lot going on here with x and y intercepts. And there's a vertical asymptote and no horizontal asymptote. Step 4, check to see if the graph crosses the horizontal asymptote. Well, there is no horizontal asymptote, so there's nothing to do for step 4 of our process. And step 5 is it's always okay to plot more points, and that's exactly what we got to do here. And that's sort of why I picked this example, because we got to do some point plotting to figure out what's going on with this graph, because all we have is the 0, 0 point and a vertical asymptote here. So I'm certainly curious about what's happening around the vertical asymptote. So let's look at x equals 2 and 4. And I'm just going to write down 3 here. Also, just we know the function is undefined when x is equal to 3. And if I plug 2 into this expression, I get 2 to the fourth over 50 times 2 minus 3. 2 to the fourth is 16 over 50 times a negative 1, right? So I have 16 over negative 50. 16 over negative 50, I used a calculator to help me if you can, if you like, is about negative 0.32. So I can approximate the location of that point. Now, I spread out the scale on my x-axis, but not on the y. On the y, it's still each square is 1. So at 2, I'm about a third, right about negative 0.3. So I'm just approximating the location of that point right there. When I plug in 4, I get 4 to the fourth over 50 times 4 minus 3. 4 to the fourth is 256 over 50 times 1. And I get 5.12 on my calculator. Okay, so at 4, I have 5.12. So 4, 5, there's 5.12, just slightly above that. Now, I would say I still don't have much of an idea of what's going on from this. So what would I do? What would I do? One thing is I want to look very close to the vertical asymptote because I want to decide, I want to choose one of these 4 shapes close to the vertical asymptote. And the way I can decide is by picking some x values really close. I'm going to look at 2.9 and 3.1. And using a calculator, it's not hard to plug these in. And I'm going to write out the calculations here. Some of the calculations here on the side. F of 2.9 is 2.9 to the fourth over 50 times 2.9 minus 3. That's 2.9 to the fourth over 50 times, now 2.9 minus 3 is going to be negative 0.1. And so you can just do this on a calculator. And just be careful. Calculator, yes, is great, but be careful. And so check that you're getting the same thing. So for instance, on my calculator, if I do 2.9 to the fourth, okay, I get that on my calculator, 2.9 to the fourth. Now, if I divide by 50 and multiply by negative 0.1, if I divide and then multiply without any other buttons pressed on my calculator, it's going to come out wrong. Here, I have to use parentheses on my calculator if I have a complicated denominator that I'm dividing by. So I can divide by parentheses 50 times 0.1 plus or minus sign changes it to negative. Close parentheses equals. And then I get the correct value. So you might just check that you're able to get these correct values, negative 14.1, on your calculator. F of 3.9 or 3.1 is 3.1 to the fourth over 50 times 3.1 minus 3. So that's going to be 3.1 to the fourth over 50 times 0.1. And I did that ahead of time. I got 18.5. I rounded off, so these are approximate. These are not coming out nice. It's negative 14.1. Now, 2.9, I'm going to write up here, negative 14.1. 3.1, 18.5. I'm not going to plot these because they don't quite fit on my scale, but those values tell me a lot about the qualities of this graph. So 3.1 is just to the right of 3. I know I'm very, very positive. That gives me confidence to draw the shape of the graph rising up along that vertical asymptote. And at 2.9, getting that negative number, that also gives me some confidence that the graph is plunging downward there. See how that determined that shape? Now, I also know I'm going from, I have that 0, 0 point, right? And this is a little tricky. I can't cross the x-axis again because I know there's only one x-intercept. So I have to kind of like just kind of creep over there to that 0, 0 point. And I'm going to have to come back down because, again, I think. And so what I want to check here is end behavior. So I don't have a horizontal asymptote, but if I plug in numbers like 10 and negative 10, they're going to give me an idea of what the end behavior of this function is, or maybe even 100 and negative 100, right? So you can also plot some more points, but I think we need to move out a bit to find out where this graph is eventually going at the extremes. So I plugged in 10 into the function ahead of time, so you can check this. I got 28.6 and negative 10, negative 15.4. And so I just want you to see how that's really enough information for me to complete my sketch now. Again, I don't have 10 and negative 10 on my x-axis, but I know from this point I just plotted here at 4 that the y values are going to be getting larger as I move to the right. And if you want to check another, another like value of x to see if you get larger, if 100 is even bigger, you can verify that. But we're going to start going up. As x goes to infinity, f of x goes to infinity. No horizontal asymptote, the graph just takes off there. And at negative 10, we're negative. That's just sort of telling me, now I don't have to get the shape perfectly. I just know the graph is going to go plunging downward now. So as x approaches minus infinity, f of x approaches minus infinity. No horizontal asymptote, but we have been able to identify the end behavior. And since we can't see my expression for the function, I'm going to recopy it right here. So not a complicated graph, but it took some point plotting because there wasn't that much information from the asymptotes and intercepts to get me started. So there's one vertical asymptote, no horizontal asymptote, just one intercept point, and there's our sketch of the graph.